Hi, Ethan. I'm back with you with 5c here. Your turn, 5c. This is the Stokes formula that they're asking about. Alrighty. So this is zeta. This is zeta, right? Zeta equals 6 pi eta a, or alpha. I'm gonna call this a. Zeta equals 6 pi eta a. All right. So zeta. Oops. Zeta. Excuse me. 6 pi eta a. Excuse me. And this is very easy. We're just going to work out what units eta is. So we have seen here that a is a radius. Now in SI units, a is in meters. So we're talking about 6 pi, which is no units at all, times eta, which is the units that we want. Oh, here. So this is some units, which we will look up in a moment. 6 pi, no units. Eta, some units. And then A. A is in units of meters. All right? Excuse me. Zeta. What are the units for zeta? So the drift velocity equals m net g divided by zeta. All right? So drift velocity, so velocity of the drift velocity equals m net g divided by zeta, right? Now we know that that velocities are meters per second. So I'm just going to get the units of zeta here. Now m is in units of kilograms, and this is units of meters per second squared, all right? And over here we're going to have zeta with units of who knows. So obviously we need one of these seconds down here, but we don't need the other one. So zeta can have second to the negative 1 power units, so that one of these seconds can go away and the other one can stay. Meters needs to stay, and kilograms needs to go away. So kilograms will cancel like this. So zeta has units of kilograms per second. Okay? So if zeta has units of kilograms per second, oops, sorry, wrong box. So if zeta has units of kilograms per second, then eta must have units of per meter per second, kilograms per meter per second. Those must be the units for eta. All right? Let's see if I can get any confirmation on that. Here we have a sedimentation time scale. S is a time. So S is a time, is a very small number of seconds, very small fraction of a second. So let's verify that we have the correct units for zeta using this. So time should equal m net over zeta. Is that true? Does time equal m net, which is kilograms, over zeta, if I have zeta being kilogram per second? Yes, it is. Kilograms cancel out, and seconds are a denominator under a denominator, so seconds go up here. So yes, we have the correct units for zeta. And if we have the correct units for zeta, then we also have the correct units for eta. So that was your turn 5c. And your turn 5c is a very kind gesture by your author here, because it tells you, what page am I on here? What page is this? Oh, okay. It's because it tells you that 5a raised a paradox. Yes, that was a paradox. Our equilibrium formula, which we calculated to be infinity, suggested that the milk should separate. Yeah, there should be none of it at the bottom and everything at the top. The fat should all be at the top. So now, why would that be? That's because that is what happens, but it happens very, very slowly. So using the Stokes formula, we can estimate how fast this happens in homogenized milk. And then we can compare that to raw milk, right? And so we're going to use the Stokes formula, and we're going to get a zeta, and the zeta is going to be in kilograms per second, and we should get a very, very small number. I mean, a vanishingly small number, I think. And then that's going to be in homogenized milk. And then we're going to try it again with with whole milk. I mean, with raw milk, with a 5 micron fat droplet size. Okay, so let's see. Stokes formula. what is going to be the eta? So A is going to be the radius, right? Is that what we said here? We have called the A the radius. Yes. So we've called the radius A, and eta. What can we use for eta? Okay, I need to look for what we use as eta, so I'm going to pause the video. Okay, here is the eta that we're going to use. The author of the book even says you should memorize it. It's 0.001. Ha 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 ha. Oh, there's pascals here. You know, I forgot to do something in part A. We have to show that that is pascals times seconds. How's the SI unit for viscosity? Show that they can be regarded the SI unit for viscosity. Okay, so we need to show that this is the same as pascals times seconds, viscosity. All right, so Pascal is pressure, right? And pressure, it comes from force over area, right? Now, area is meters squared, and force is newtons. But 1 newton is really the acceleration of 1 kilogram by 1 meter per second squared. Force equals mass times acceleration, yeah? So what is this? So what does this boil down to in terms of units? Well, one of these meters cancels with one of these meters, and these seconds go down here. So it's really kilograms per meter per second squared. That is what a pascal is. So 1 pascal is 1 kilogram per meter per second squared. But we have kilograms per meter per second, not per second squared. So we need to multiply this. So multiply both sides by a second. Right? So this is now kilogram over meters over seconds. That's what we have. Kilograms over meters over seconds. So that means we need seconds times Pascal. So that shows that the SI unit for viscosity, and this eta is apparently the fudge factor to express viscosity, is pascals times seconds. All right, now let's get on with B over here. I think I need another paper, so get another paper here. So I needed to get the eta, yeah. Oh, so we found the eta. So zeta, it's like a frat house, or it's like a Greek convention here. Zeta, eta. We should just call that A alpha instead of A. All right, so that equals 6 pi times the eta, which is 1,000th, right, times the A. Now the A is really small. It's the radius, isn't it? And from our previous work, we saw that the radius was 0.5 microns for the homogenized milk. So that was 5 times 10 to the minus 7 meters. That's 0.5 microns. All right. So that's for the homo milk. Now, what about the raw milk? The raw milk, zeta, equals 6 pi times 0.001 times 5 microns. So 5 times 10 to the minus 6 meters. So raw milk separates 10 times faster than homogenized milk. 10 times faster. So if it takes you 1 day to let the raw milk separate, then it would take you 10 days for the homogenized milk to separate. Now, I have kids, and we drink milk, and there is never a case when the milk is in the fridge for 10 whole days, because at that point, you gotta throw away the milk. All right, so you can get to a number here if you like, and the units for that number, of course, will be this, kilograms per second. So it will be some very small number of kilograms per second. Actually, I would like to see what that number is. 6 times that many kilograms per second. The fat is separating in our milk that many kilograms per second. Okay, what is this in grams? That many grams per second. That's 9 micrograms. So Ethan, the milk in your fridge is separating at a rate of 9 micrograms per second. Well, the fridge is colder than room temperature, and we have used the eta for room temperature. So it's even slower in your fridge because you probably have a higher eta. Higher eta? I mean a lower eta. You have a lower eta in your fridge. So it's even slower in your fridge. 9 micrograms per second. What about the raw milk? The raw milk is separating at a rate of 90 micrograms per second. Huh. Yeah, I still kind of don't believe that. Well, this is a simplified view of milk. The solutes in milk are not actually just fat droplets. I mean, what if you have non-fat milk, right? They're also proteins, and the proteins have a non-polar part and a polar part. And so, since those proteins are double-headed in that way, they help the fats to stay in solution. So this your turn problem is an oversimplified case of milk.